Hello, this video is going to talk about the titration of a strong acid with a strong base and why this curve has the shape it does and how to go about solving for pH at various points along a curve like this, at various points during your titration. So in this case, our example is titrating hydrochloric acid, that's what's in your beaker, and adding sodium hydroxide to it, that's what would be in your burette. So we can look at the equation two different ways. One would be the molecular equation, which kind of shows everything. So that would be HCl plus NaOH makes NaCl plus H2O. This looks like a double displacement reaction. This thing right here we make is called our salt, and we make water. So acid plus base makes salt plus water. The net ionic equation gives us a more accurate picture of what's actually reacting in the solution. So what's actually happening in the solution is your H plus ions and your OH minus ions are reacting to form water. The sodium ions, the chloride ions, they're just hanging out, not doing anything. They are spectator ions. So what's happening is our acid and our base are going to neutralize and form water. Okay, so we'll think about the shape of the curve and how to find pH along the way. So initially, at this very first point, we have pure strong acid. So in this case, we're saying we've got 20 mils of pure 0.1 molar HCl. So how do you find the pH here? Well, since it's a strong acid, that means it completely dissociates into ions when you dissolve it in water. Therefore, your concentration of your strong acid is equal to your concentration of your H+. Meaning, if I have 0.1 molar HCl, really what I have is 0.1 molar H+ ions and 0.1 molar Cl- ions. So when I find the pH of a strong acid, it's one of our simplest calculations we can do. We just say the pH, since the pH is the negative log of the H+ concentration, and we just said H+ concentration is equal to your acid concentration when it is a strong acid, that means the pH equals the negative log of my concentration of strong acid. So in this case, it equals a negative log of 0.1 molar. We don't use Ka or Kb values here because these are strong acids and bases. We only use Ka, Kb if we're dealing with weak acids or weak bases. Okay, so then if you go along the curve here, let's say that we stop here and say, what's my pH at this point when I've added 15 mils of 0.1 molar NaOH? So I'm not quite at equivalence yet. I've added some hydroxide, so some of my H+ ions have been used up, but I still have some left over. So I still have some H+ ions floating around. So what that means at this point is I have excess moles of hydrogen floating around in my solution. All the OH I've added has turned into water. So to figure out what my pH is at this point, I want to figure out how many moles of excess hydrogen I have. So what I would do is I would look at how many moles did I have initially in my beaker. I'm going to subtract from that the number of moles of OH I added. That will give me the moles of hydrogen that I have in excess. And then once I have that, I'll take my moles of hydrogen and divide it by my total volume to get my hydrogen ion concentration, which I then can plug into this equation to find pH. So if we want to take this and do this as an example with our actual numbers here, my moles of H+ initially, I would find that by taking my molarity and my volume of my initial solution. So I have 0.1 molar, 0.002 milliliters. That means I have 0.002 moles of H+ to begin with. Again, I got that from 0.10 molar times 0.02 liters. So that gives me my initial moles of H+ ions. Then I'm going to subtract from it how many moles of OH I've added. So at this point, I have added 0.1 molar base, and I've added 0.015 liters of it. So I've added 0.0015 moles of OH. Those 0.0015 moles OH will react with 0.0015 of my hydrogen moles, leaving behind 0.002 minus 0.0015, which is 0.0005 moles of H+. So I've got 0.0005 moles H+ in excess at this point. It's still present in my solution. To find the H+ concentration, I want to take those moles and divide it by my total volume. And here's where you have to pay attention with what you've added, and keep in mind that this volume is additive now. So I started with 20 mils, I added 15, so now my total volume is 0.035. So make sure you add together those volumes. And let's stop and solve for this. You end up with 0.0005 divided by 0.035. That gives you an H plus concentration, I should label this, of 0.014 molar. So to find the pH, I take the negative log of this number, and I find the pH is 1.85. The thing I want to point out is even though I've used up a majority of my hydrogen ions, right? I've used up like 3/4 of my hydrogen ions. My pH did not change by very much, and that's because pH is a logarithmic scale. So it's going to be pretty flat here at the beginning, because even if I use up half or 2/3 or 3/4 of my hydrogen ions, I won't see much of a change in the pH, because to get the pH to change by 1 unit, I would have to, my hydrogen concentration would have to go down tenfold. So I'd have to use up 90% of my hydrogen before I see a pH change of 1 unit. So it's going to stay pretty flat for a while. Okay, until I get at my equivalence point, and all of a sudden it starts to change rapidly. At equivalence, equivalence is the midway point of your vertical region. At equivalence in this case, it will have a pH of 7. So if I went over here and looked on my graph, I'm going to draw a little dotted line, we would find it has a pH of 7. The reason why is because at equivalence, all of your hydrogen has reacted with hydroxide, leaving behind water. The other ions that are present in your solution are sodium and chloride. And if you remember back to when we talked about the pH of salts, we know that sodium chloride is a neutral salt. So this does not affect the pH. So essentially what we have is pure water, which has a pH of 7. Keep in mind this is only true for strong acid, strong base titrations. If you started with a weak acid or a weak base, you will make a salt that is not neutral. And so your equivalence point might be above 7 or below 7. So just keep that in mind. At the end, after equivalence, it's very similar to this scenario over here, except instead of having excess hydrogen, you will end up with excess hydroxide. So we've already, all the hydrogen we started with has already been converted into water, but I'm going to keep adding sodium hydroxide to my mixture, so the pH is going to shoot up here. What I'm going to have present in solution at this point will be sodium ions, chloride ions, as well as hydroxide ions, extra hydroxides floating around, along with water. So I've got excess moles of hydroxides floating around. That's what's making my pH high. So the way to determine the pH after equivalence is similar to what we did here. You're going to say, how many moles of OH did I start with by taking my, how many moles of OH have I added by taking my volume times my molarity. So let's say we added, 30 mils of hydroxide. I would take my 0.03 times 0.1 molar. That would give me how many moles of hydroxide I've added. I would subtract from that the initial moles of H plus I started with, which we found over here. It would be 0.02 moles. And whatever's left over would give me how many moles of excess hydroxide are floating around. I would take that excess moles of hydroxide, divide it by the total volume. Again, I have to add together the volumes that I've mixed, so it might be 20 plus 30, might be 50 mils total. And that would give my hydroxide ion concentration. So you could take the negative log of this, would give you your POH, and you'll have to use this relationship. Remember that pH plus POH equals 14. So once you find POH, then you could solve for pH using this right here. So this is a titration of a strong acid with a strong base.